Okay, so welcome to part 7 of Negative Sequence Made Easier. This is actually going to be 7A. We're going to break this into 2 different videos because this relay's got a lot of math that's going to be ridiculous, and I'm going to save that calculation for the pickup for part 2. So this is going to be over the IQ 1000 relay. This was originally by Westinghouse, and then that was the 1000, then the 1002 by Westinghouse, then Cutler Hammer bought the model, and then Eaton had it. So I mean, it's had a lot of manufacturers, but the original manual that came with this has a really good description for negative sequence and positive sequence currents in a motor and how they affect the motor. And so generally in a motor, what you would have is you will have always, you should want to have your I1, which is your positive sequence currents. And ideally, I mean, you're probably going to have some kind of unbalance, but ideally that I1 current, the positive sequence, would be much, much greater than your I2, which is your negative sequence currents. Okay, and what it is saying is right here, the positive sequence, since it's much, much greater, it obviously wins, and the positive sequence currents cause rotation in the positive direction, which is torque on the motor, which is great. That's what you want. Your work, your work and energy that you're putting into this, the power, is being converted directly to torque. However, you also have an unbalance of the voltages, which causes some kind of negative sequence, and the negative sequence is going to try to cause torque in the opposite direction, which is what's listed right here. But because the torque generated by I2 does not leave the rotor, it can't because the I1 wins, right? The positive sequence is winning. That I2, that negative sequence current turns into heat, and that is a problem. So they use a calculation to calculate how much heat is being generated by the rotor, and that's what this equation is essentially doing. And so that's what's going on here. Now, I've taken all this data from the manual, and it says that the pickup is essentially going to be this kind of a calculation right here. I know this isn't exactly right. Don't look at this and think that Tommy made a math error. Okay, but the pickup, which is PU, is going to be this. It's going to be dictated by this equation. Okay, and we're gonna break that out here in a second. And then they tell you that in order to figure everything out, you're going to need all of this great data, which a lot of it's really just for the time delay, and we'll talk about that shortly. Okay, so let's talk about the pickup and define it first. But in order to, I mean, what I told you that the math I was going to fix it, right? This right here is essentially I took the square and I just square rooted all of this to make it equal, and that's what's going on this one here. Okay, so the pickup is equal to your FLA times service factor. I'll show you that later, but that's what it is. And so that's what this is going to be. But they're using some kind of a square calculation. So in order to get rid of that square, we put the square root over here. That cleans up the equation. I can define all of this, and this by what I inject into the relay. What I can't do is define what this K value is. So we need to find out what K is, and that began the quest for K. So I searched a lot of manuals, the IQ 1000, the IQ 1002, a lot of manufacturers and distributions, and I came up at a loss. I really did. And so I emailed Eaton, who owns the series now, and they said that the IQ 1000 was replaced eventually by the MP 3000, which was later replaced by the EMR 3MP0 relay. And they have it in their manual listed here. And I was like, that's great. K is defined, but I want to see it. So I opened up these manuals, like he said, and then this one. And so I got to it, and yes, the 3000, great. It says it's a direct replacement, and down here it says it follows the same thermal curves. That's great. And you look in there, and it's got all the same equations and calculations, and that makes you feel really good. These are just positive and negative sequence. That's not going to change, but this one right here, that's the money. Okay, so that's the exact same calculation. So that's great. This is the same calculation, so he's not lying to me there. Didn't think he was. I just need to see it. And so I looked in this manual, couldn't find a lot, but it wasn't actually the operator's manual. It was something else. But they did allude to that it has the same K values or the same calculation, but not defining what it is. And then I found this manual, which is great. This manual actually had a lot more legible curves, and they all matched everything almost exactly to a T from the first IQ 1000. So I mean, this is all the same stuff from the IQ 1000. So that's great, but no K. And then you dig deeper and you find here's the equation that he sent me a screenshot of, and yes, K is defined. So perfect. That's awesome. The equations are all the same, and k is 6.01, so perfect. So now we've solved for k. That's important because we can determine what our negative sequence is and our positive sequence, but we need that value to be able to figure out what our true pickup value is going to be. Okay, so that's perfect right there. And let's figure out the last thing. I did tell you earlier that that initial this I2 is going to be essentially your FLA times your service factor. Okay. And this is the original equation that they gave you. And I'm telling you that I found it, and it's right here combined with this information right here. And it says ultimate trip level is 100% of FLA. Okay. Now, it also says right here, if the motor has a service factor larger than 100%, the ultimate trip level can be increased accordingly. A service factor of 100 or 1.25 can be used with 125% ultimate trip level. Okay, so that's all that's trying to say is that essentially your pickup really, your ultimate trip level is going to be FLA times service factor. And that's only if you have 100% positive sequence. Okay, because if you had, I mean, if you go ahead and you were to have 0 negative sequence, then everything on the right hand side right here cancels out, and then this is just positive sequence squared, and then you square root it, so it becomes the exact same number. Okay, and so this would equal your I1. All right, so everything lines up and it all feels good. What we do have left, though, that I do need to be quick about going over is our time delay. So we just need to figure that out, and that's what the rest of this stuff is used for. We're good on all of this and this, but we need to figure out that time delay. And the time delay actually is not too terrible. It was all in the original first manual. You just have to realize that time delay is going to be t equals x divided by I2. You have to define x. X is actually a combination, like they told you earlier. You're going to need your FLA, you're going to need your locked rotor current, and you're going to need your stall time. And so it's just a combination. It's going to be your locked rotor current, the multiple of FLA for your locked rotor current. So here they're saying L, your locked rotor current is going to be 6.1 times FLA. So it's going to be 6.1 squared times 15 seconds is what they have. And that's how they got this right here, which is 558. So X equals locked rotor current squared times the stall time. And then this I, well, that I is going to be a multiple of FLA. Just like you test anything else for the most part, you're always doing multiples of tap for overcurrent. Now be careful. It's not going to be FLA times service factor. Okay. Service factor only sets the initial pickup. Okay. That's all it does. It sets this initial line. The whole rest of the curve is always going to be, all these lines are in multiples of FLA. Okay. So now we've got this 100% defined. And like this is the total, all of the definitions. So if you want to calculate something yourself, you can. But this is exactly what we need from the book. So we're going to do a quick example of time delay for this one. And going forward, what I do want to say is that when we do our pickup calculation, I do all of my current unbalances testing and negative sequence testing for motors. I test them using these steps right here. So we're going to keep all magnitudes at FLA and only increase one above FLA, and all angles will stay balanced. Okay. I have really good reasons for why. It makes the math easier for some, and it's just a standardization that I do. But let's go ahead and calculate this stall time real quick. I'm sorry, this time delay. And so the time delay essentially is going to be TD equals, and I have the example right here, locked rotor current is 6.5, so it's 6.5 times 6.5, if I could write 6.5, times the stall time, which is 11 seconds, divided by 2 times 2, because we're testing at multiples of FLA. We're going to be testing, as testers, we can define where we test. So that's where we're hitting the curve. And when you do the math and divide this out, what you get is 116.18 seconds, and that's when it should trip. Okay, which is quite a long time. So if you wanted to sit here and change some stuff, then you could. But remember, this is stall time, locked rotor current setting is squared, and then your multiple of FLA squared. There is no service factor. And in the next one, we'll go over how to calculate the pickup. It's going to be absolutely ridiculous. So strap yourself in for a lot of vector math.